Hi everybody, and welcome to the real meat of the lecture on section 7.5, which is applying the triage process that we introduced in the first video to actual integrals. To start with, let's look at this one. The first thing that you should notice is that it looks like this is probably ideas from 7.2, that is products and quotients of trig functions, but it doesn't follow any of the special rules that we saw because it's a quotient of trig functions and not a product. The first thing I'm going to try is some algebra to see if there's anything that simplifies. And I look at it and I say to myself, all right, well, sine over cosine is tangent, but then I have a sine squared left over, and tangent and sine squared don't really mix together in a good way. The next thing I might think is there an obvious substitution that I can make? So I might try, so I'm just going to try the obvious substitution, which is to let u be equal to the cosine of x. Now, why cosine and not sine? Because cosine is in the denominator of the fraction. So I don't want to let u be equal to the sine, because if u was the sine, then du would be cosine x dx, but the cosine is trapped in the bottom. If u was equal to the cosine of x, then du would have to be minus the sine of x dx. And I think to myself, right, I've got 3 sines up on top here. I've got a sine cubed, and the du will absorb one of those sines, but then I'm going to have these extra 2 sines left over. Is there anything that I can do to fix that? And the answer is, I can use a trig identity. The fact that I know that I need to have a sine x to be the du for this particular substitution motivates writing the integral this way. Maybe what I could do is write sine squared times the sine of x over the cosine of x dx. This piece is going to be used in a du. So this sine x dx right here looks almost like a du. And this piece right here, this is a u. So what about that? How can I undo that and make it fit with this substitution? And the answer is, I can use a trig identity to turn this sine squared into cosine squared. And now I'm completely set up to make this substitution go. So you should see that after the substitution, what you're going to get is the integral of 1 minus u squared over u times minus du. And that integral is actually very easy to do because it turns into the integral of 1 over u minus u, and then there's a negative that comes out front from the du. And you can integrate using the power rule and the fact that the integral of 1 over u is the log. The next integral I want to talk about almost looks like an integral of trig functions, except there's this t in here. Now, the fact that there's a t means that we're not going to be able to do any sort of clever u substitution, because a u substitution where u is equal to sine or u is equal to the cosine is going to give me a du that also has that, and then there's going to be this t floating around. The t isn't going to cancel when I do that. So a u substitution isn't going to work. There doesn't seem to be any obvious algebra. So because I've got trig functions, the next thing I do is I start looking for an obvious identity. And one of the identities that's really useful in these calculus classes that perhaps you don't remember or haven't seen in a while is when I see products of sine and cosine, I can convert those using the sine version of the half angle formula. So I'm going to use the fact here that sine t cosine t is equal to the sine of 2t. And this problem then becomes t times the sine of 2t dt. And now I've got a problem that fits into my triage process because this is an integral by parts. And I know it's by parts because I have a polynomial times a transcendental function. So this is parts. The process for this problem is going to be to let u equal t so that du is just dt, and then dv is the sine of 2t dt, and so v is equal to negative 1/2 of the cosine of 2t. And what you end up with is minus 1/2 t cosine of 2t plus the integral of 1/2 of the cosine of 2t dt, and that integral is easy. Okay, so we triage this problem first by applying some kind of algebra, and then after we apply the algebra, we end up with a problem that we can do by parts. And recognizing how to make that move is important. For our third problem, Let's look at something that looks a little bit more complicated. To my eye, this almost looks like a trig substitution, except I have these logs floating around instead of x's. And that's obnoxious, because I can't use inverse trig substitution unless I've got a squared plus x squared. So this almost looks like a tangent substitution. So maybe I can change this exercise from something nasty into something nice by using a u substitution. The obvious substitution to try here is to get rid of the natural log. So I'm going to let u equal the natural log of x, and then maybe it will turn the problem into something nice. If u is equal to the natural log of x, then du is 1 over x dx. And now I feel fortunate because I have a 1 over x dx in the problem. There's a 1 over x right there since it's in the denominator, and here's the dx. So with this substitution, this problem becomes the integral of u over the square root of 1 plus u squared du, because dx is equal to x du, which cancels the x's out. So a u substitution gets us into this form. Now you think to yourself, okay, what can I do? It looks like a trig substitution now, because now I've got the form on the bottom where I've got this radical and I have the 1 plus u squared, so let's just do an inverse tangent substitution. You can do it that way. Let me stop you for a second and remind you that the next step after you've done a transformation is always to check and see if you've made another substitution possible. What you should notice here is this problem can also be done with substitution, because if I let v equal to 1 plus u squared, then dv is 2u du, and I have a u du right here. So I can do a second substitution. V is equal to 1 plus u squared, so dv is 2u du, which means dv over 2 is equal to u du, and this entire integral can be transformed one more time into 1/2 times the integral of dv over the square root of v. And this integral is easy. Now, on these problems, I'm leaving it when we get to the point where the integrals are easy, because I want to focus on the transformation from a nasty integral into something that we already know how to do. This can be done using the power rule, because this is just 1/2 times the integral of v to the minus 1/2 dv. You can use the power rule to do that. At the end, you just have to remember to substitute back twice to get back to an integral in terms of t. The next integral I want to talk about is one that is going to require some factoring. So here we have an integral that just screams out for partial fractions. And the reason it screams out for partial fractions is because this is a rational function. You should check first that there's not an obvious substitution. And the answer is no, there is no obvious substitution. The obvious substitution here would be u is equal to x to the 4th minus 16, but then du would be 4x to the 3rd dx, and I don't see an x to the 3rd up here. So this isn't going to work. The next thing to try would be to say, well, it's rational. I've classified this as a rational function, and when I have rational functions, I need to use partial fractions. X to the 4th minus 16 is a difference of squares. So this is going to factor as 1 over x squared minus 4 times x squared plus 4. And x squared plus 4 is irreducible. You can check that, because if you solve for x, you would get plus or minus 2i, which is complex numbers, and we're not doing complex numbers. X squared minus 4 is another difference of squares, and so this can be written one more step as x plus 2, x minus 2, x squared plus 4. And from this point, you can actually use partial fractions, because now we've got it factored out into linear terms and an irreducible quadratic. So the integral of 1 over x to the 4th minus 16 is the same as the integral of 1 over x plus 2, x minus 2, x squared plus 4 dx. And now we just need to write down the partial fraction decomposition. 1 over x plus 2, x minus 2, x squared plus 4 is equal to a over x plus 2 plus b over x minus 2 plus cx plus d over x squared plus 4. And from here, I'm going to assert that this integral is easy, because I'm going to find the a, b, c, and d using whatever technique that we have available to us. And then after I find a, b, c, and d, I can integrate each of these pieces because this is a log and this is a log, and this is going to turn out to be something like a u substitution and then an arctangent. So this is all in the technique of 7.4. So I wouldn't consider this integral easy in the way that the previous ones were, but I'm going to write that it's easy because it's a technique that we already have studied. As the final example of this triage section, let's look at a slightly more complicated example. So this integral doesn't appear to be in any of the forms that we've looked at all. It doesn't look like a rational function because there's those e's running around down there. It's certainly not a trig function. It doesn't seem like it has an obvious u substitution, so we need to know what to do. In a problem like this, you might think, okay, can I use integration by parts? The problem is that you're not going to make anything better because you've got 1 over this, and taking its derivative is going to make an even nastier problem because the quotient rule is going to be involved. In a problem like this, one of the things that you should try is to reduce the complicated parts to simpler parts with a u substitution if you can make it work. When I look at this problem, I think the issue is I have these e to the x's floating around. Can I get rid of them? And in particular, the issue is I have these e to the x's where this one is e to the positive x and this is e to the negative x. Other than that, it's almost like a rational function because it's 1 over a pile of things that kind of look like a polynomial, except there's those e to the x terms in there. So maybe I can get rid of the e to the x terms. Let's just try and see. It would be nice if I could let u be equal to e to the x, so that du was equal to e to the x dx. You don't have an e to the x in the top of the function, but maybe we can just try the substitution anyway and see if somehow magically it works out. When you're doing integrals like this, a lot of times you just have to try things and see if they work. Du over e to the x is going to be equal to dx. So let's try the substitution and see if the algebra cancels. If we do that, what we end up with is the following. We have 1 over 1 plus 2u minus u to the minus 1, because that's really a 1 over e to the x right there. And then dx got replaced with du over e to the x. And you think, shoot, I still have this e to the x floating around. But e to the x is actually u. This might feel like cheating, but if you've got a substitution, you can use it. Now what? Well, now we're going to do more algebra. We're going to take this u and we're going to multiply it in to the polynomial down here. And what you get is 1 over u plus 2u squared minus 1. And that problem is a partial fractions problem because this factors as 2u plus 1 times u minus 1 du. So this is partial fractions. So don't give up. When you're looking at a problem, even if it seems like the idea might not work, if you have nothing else to try, try something. Try a u substitution. Try some algebra. Notice that even though I did not have what I needed to make the dx right here, I still got it because when I did this substitution, dx is really du over u because I have a substitution for u. I'm going to encourage you to do as many of these exercises as you can stomach doing. Integration is an art that is learned by practice. So I'm going to assign more homework questions than usual, and I'm going to do less lecturing because I want to focus on how to solve these integrals when you see them without being told how to proceed. Okay, good luck.